Hi everyone, this is Stephanie Quigley, and this is my wall insulation mini design project for Challenge Assessment 2. The objectives are to model a scenario as a thermal resistance network, and my model is right here. Next is to calculate the heat transfer rate, then find the temperatures at the edges of different mediums, which would be right here is 1, 2, 3, and 4. Next is to change the parameters and analyze the effects, and also change the material of the insulation and analyze those effects. And finally, I will talk about redesign. First things first is to find the thermal resistance network, and to get to my network here, my R1 is here, which branches off into parallel R2, R3, and R4, which then combine to R5, and that's what we see here. This is our equation down here, RT, to find our total resistance. So we need to add R1 plus our resistances in parallel plus our R5. And to find our parallel resistances, I would use this equation up here. And to find R itself, we're going to do the thickness is L, which is these distances right here. Then we're going to find the thermal conductivity, which is given to us. And then also this is our surface area, which is actually this spot over here, which is given to us as 6 meters, and this is 4. So that is how we find our resistances, and our total parallel resistances came out to be 10.0395 watts per Kelvin, and we plug that in down here. And then once we add those up, our total resistances become 0.0997 watts per Kelvin. Next, for our heat transfer rate, we use this equation right up here, which is Q dot is equal to change in temperature over total resistance. I'm given the total change in temperature, which is 22 Kelvin. It actually says in the problem that the difference is 22 degrees Celsius. Because it says difference, the difference is the same thing in Kelvin. The difference is 22. So we're going to have Q dot is equal to our 22 Kelvin divided by our resistance that we found in the other slide, and it comes out to 220 watts. Next, we want to find the temperatures at each material. So this is how I divided up. I did outer wall 1 as 1, inner wall 1 as 2, inner wall 2 as 3, and outer wall 2 as 4. And to find these temperatures, this is the equation that I used here. And this should actually be temperature 2 is equal to Q dot times R plus temperature of 1. So the very first outer wall temperature I chose, and I chose it to be 293 Kelvin. So I'm going to plug that into T1, which will then give us our T2. And that goes into our inner wall 1. Then we take this inner wall 1 temperature, plug that into our T1, which gives us the next T2, our inner wall 2. And we do the same thing to get our outer wall 2 to equal 315 Kelvin. And down here in this graph is just a visualization to see what's happening. Outer wall 1, 1, inner wall 1 is 2, inner wall 2 is 3, and the last one is 4. And we can just see that the change in temperatures here between 1 and 2 is very small, but there is a change, same with 3 and 4. The first parameter that I changed was adjusting the thickness of the middle layer, and that is this thickness in here. And so that would actually change the thickness of R2, 3, and 4, which would then change our resistances in parallel, which obviously would then change our total resistance, and our Q dot, which is what we're looking for. And so I found that changing the thickness of the middle layer, as we increase the thickness, it actually decreased the heat transfer rate. And you can see that trend here in this graph. The next parameter change, I adjust the length of the wall, and that one is actually this parameter right here. So it was 6 meters. So then when we did that, it would change every single one of the resistance values, and then which would then obviously change the parallel resistance and our total resistance, which will then change our Q dot. And I found that as you increase the length of the wall, the heat transfer actually also increases. Finally, the third parameter I changed was adjusting the thickness of outer wall 2. So that would be this right here, just this thickness, which just changed the resistance of 5, which changed our total resistance and our Q dot. So as we increase the thickness of the outer wall 2, you can see the trend where the heat transfer decreases. I also changed the material of the insulation, so I used chalk, natural rubber, asphalt, and then fiberglass was what we originally started with. And in this graph up here, thermal conductivity versus heat transfer, you can see a positive trend between thermal conductivity and heat transfer rate. So as you increase the thermal conductivity, so does it also increases the heat transfer rate. So when we started with fiberglass, I had the lowest thermal conductivity, which also had the lowest heat transfer rate. Down in this graph was different material, just another visualization to be able to see the different materials and how their K value affected the heat transfer rate. Finally, I want to talk about the redesign. So the goal is that we want a low heat transfer rate. And the first thing you can do is increase the thickness of the middle layer, which is right here. And as we increase that thickness, it actually increased the total resistance, which then decreased our heat transfer. We also wanted to keep the length of the wall short, which is this dimension right here. And keeping that short makes the surface area decrease, which then increases the resistance. And with the resistance increasing, our heat transfer rate would decrease. Thirdly, we increase the thickness of outer wall 2, which is this dimension, and also as we increase that, our resistance went up, which decreased our Q dot. And finally, you want to choose an insulation material that has a low thermal conductivity because that will have a lower thermal resistance. And that's all I have. Thank you very much for listening.